Hey guys, hope everybody's doing okay. What we're going to do today is take a look at the end of our intermolecular forces discussion, and we're going to focus on factors affecting solubility, enthalpy of solution, and colligative properties. Three relatively short topics that are all greatly affected by intermolecular forces and the strength of intermolecular forces. So we're going to get started by looking at factors affecting solubility. What would cause something to be more or less soluble in some solvent? And then we'll move on to the enthalpy of solution, which is the change in heat when something dissolves. And then finally, colligative properties to wrap it all up. So before we get started with that, something really important I want to make sure I mention. Back in Chem 1, back in baby chem, when we were trying to explain solubility, if something was soluble or not, we might say like dissolves like. That's our solubility rule. This is the last time we're ever going to say that. Okay, so never say like dissolves like in an AP chemistry class for as long as you live. Okay, you will get 0 credit on any exam or quiz that I give. You'll get 0 credit on the College Board exam if you justify something dissolving with the term like dissolves like. Okay, so never say it ever again. What you need to do is describe the force of attraction between the solute and the solvent. Okay, so if you remember from the one of the previous lessons, something's going to dissolve in something else if the forces of attraction are relatively similar, right? So that's why polar dissolves in polar. Say you have some sort of rubbing alcohol, okay, that's polar, that will dissolve in water because it's also polar. So there's some forces of attraction between those two liquids that will cause one to dissolve in the other. Something that is nonpolar, like oil, won't dissolve in something that's polar because the oil has London dispersion forces and the water has hydrogen bonding, a very, very polar, attraction there. So there's no way that the oil, which is nonpolar, will be attracted to the water, which is polar, because those London dispersion forces won't be attracted to those hydrogen bond forces that water has. Okay, so something will dissolve if the forces of attraction are relatively similar. Something will not dissolve if you have two very different intermolecular forces in play. All right, so you need to compare the strength of the attractive forces within the solute and the solvent in order to properly answer one of those questions. Okay, since a lot of this final lesson here is focused on solubility, I wanted to make sure I mentioned that. And I'm sure I'm going to mention it a million times in class too. But like dissolves like is no more. All right, never mention that ever again. So there are two factors that affect solubility. One of them is temperature. So I'm sure we're familiar with this. What effect would increasing the temperature have on the solubility of a solid or liquid in a solution, in another liquid, and why? So you're probably used to this if you want to dissolve sugar in iced tea versus hot tea. It dissolves a lot easier in hot tea. So there's really nothing to memorize here. You just use some common sense and some everyday observations that you know. But we need to be able to explain why at a higher temperature, solids or liquids even would dissolve better. They'd be more soluble than at a lower temperature. So just think about what happens at a higher temperature. At a higher temperature, particles move faster. So there's a faster rate of movement, okay, and a faster dissolving rate because there are more frequent collisions. So the solute and solvent, if they have those similar forces of attraction, will collide more often, and they'll be able to interact more, right, and therefore dissolve better. So we've known from Unit 1 in Chem 1 that at a higher temperature, particles move faster. You're just applying that knowledge to this scenario. So the amount of solute, that's what you're trying to dissolve here, capable of being dissolved, will be increased because the collisions have more force and they're easily, you can more easily break forces of attraction between the solute and the solvent, right? So in order for something to dissolve, the attractive forces in the solute need to break. The attractive forces in the solvent need to break. And the attractive forces between the solute and the solvent need to form, right? So if everything is moving faster and colliding more, you could easily break those forces of attraction in the solute and in the solvent, so the solute and solvent can come together with their forces of attraction. Okay, so general rule for most solid liquid or liquid-liquid solutions, increasing the temperature increases the solubility. What effect would this have on the solubility of a gas, though? This is the opposite. So for gases dissolved in liquids, think of carbon dioxide dissolved in like soda, right? Increasing the temperature will decrease the solubility of the gas. Well, why is that? Again, go back to what we talked about on the previous slide. Particles move faster, right? If the gas particles in your soda are moving faster, they'll be allowed to escape easier, right? It'll be easier to escape the soda and go into the atmosphere. And then when there's no gas left, when there's no CO2 left in your soda, it's flat, right? So the same situation as the previous slide, the same scenario is in play here, except instead of increasing our solubility, it's going to decrease our solubility of gases because those particles are going to leave and they're not going to be in solution anymore. So this is why soda is kept in the refrigerator to keep more CO2 dissolved in it. So at that lower temperature, particles are moving slower. The carbon dioxide is not escaping as readily. So your soda stays carbonated for a longer period of time. Cold water also has more dissolved oxygen than warm water. So cold water fish require more dissolved oxygen. So cold water fish need more dissolved oxygen, which is good because in colder water, the oxygen gas will stay in the water. It'll stay dissolved in the water, and it won't escape into the atmosphere. So if there's something related to climate change, if some of these cold water locations are increasing in temperature, that doesn't bode well for some of the fish potentially living in those waters, right? Another factor that affects solubility is pressure. Pressure is going to have no impact really on solubility for solids and liquids. So if you want to dissolve sugar or salt in water, increasing the atmospheric outside pressure is not really going to change anything about that. Okay? The main impact we're going to have here is on gases, though. So the greater the pressure of a gas above the liquid, the greater the solubility. And there's a key word here. You might not think is important, but it is. It's right here. Okay? The greater the pressure of that gas above the liquid, the greater the solubility. So if you want to increase the solubility of a gas, you want to increase the pressure of that gas above the solution you're trying to make, right? So think of a bottle of soda, right? It's pressurized. When you open that 2-liter bottle of soda or a can of soda, you hear some of that air escaping, right? So soda is capped under high CO2 pressure. So more CO2 will stay dissolved. So carbon dioxide is what gives you the carbonation in soda, right? The carbon dioxide is dissolved in the soda. So in order to increase the solubility, keep it dissolved. That's why the soda can sit on the shelf for so long and not go flat. And when you open it, it starts to go flat. It's because it's capped, it's pressured, it's pressurized with carbon dioxide, the same gas that you want to dissolve in the soda. The partial pressure of the gas dissolved matters, not the total pressure. Okay, so not the total pressure. It's really just the partial pressure of the specific gas you want to dissolve. So the fizz keeper, remember using that in a lab in Chem 1 within the gas law unit. The fizz keeper is where you just pump regular air into a soda bottle, and it's supposed to keep it carbonated longer. They don't really work because the carbon dioxide is what's in the soda, right? That keeps it, that makes it carbonated. When you're if you're using this fizz keeper to pump gas into that soda bottle, 80% of the atmosphere is nitrogen, 20% is oxygen. So 99% of what you're pumping in is not CO2, right? It's not what you want. So it's not really going to work very well at all. It might have a minuscule impact. Scuba divers, if they surface too quickly, can get something called the bends. That's when the nitrogen that's dissolved in their blood will start to come out faster. So you have to go back to the surface very slowly. If you go too fast and the pressure decreases, right? Because as you go to the surface, you don't have that high pressure anymore. Under the water, it's extreme amounts of pressure, right? Keeping that nitrogen dissolved in your blood. As you surface and the pressure decreases, the gas can escape easier, and it can be very uncomfortable and very painful for scuba divers when that nitrogen gas starts to leave their blood too quickly. Okay. Okay, so that was a quick 10-minute lesson on factors affecting solubility. So here's our general summary. You want to memorize your solubility rules from the previous lesson. So group 1 metals, NH4+1, and some of our polyatomic ions are always soluble. You want to make sure you could quickly identify those. Again, you're never going to use like dissolves like ever again, so you want to mention your solute-solvent interactions. Mention this when answering the FRQs about solubility. So I talked about that the very first 3 minutes or so of this lesson. And then you want to make sure you understand the difference between the pressure impact on solubility and the temperature impact. So pressure will have very little effect to no effect on solids and liquids, but it has a large effect on gases. But it has to be the same gas above that's pressurized that you want to be dissolved in your solution. Temperature will have the same effect on solids in liquids and liquids in liquids. Higher temperature, greater solubility, and the opposite effect for gases. The greater the temperature, the lower the solubility of gases. Particles can escape a little bit easier. So once you have your solution made, or actually when you're making your solution, you might have a change in temperature. So that's called enthalpy of solution. We'll talk about this more in our thermodynamics unit a little bit later on in the course. So in order for something to dissolve, 3 steps need to occur, right? So step 1, we need to break the interparticulate forces within the solute. So here are 2 examples here. There's an exothermic and an endothermic solution. So sometimes you dissolve something and it gets cold, that's endothermic. Sometimes you dissolve something and the temperature goes up, exothermic. So the first step of dissolving is to break, I mentioned this a couple slides ago, you're going to break the forces of attraction in your solute, okay? You also want to break the forces of attraction in your solvent. So there's a good image of that here. So you have your solvent, water, most likely. Particles have hydrogen bonding. You need to break that hydrogen bonding in the water, okay? Your solute, let's say it's table salt. You're going to break the ionic bonding in the table salt, okay? That requires energy, okay? So look at step 1 and step 2, breaking your solvent and solute forces, right? That's step 1 and 2 here. Both of those are endo, okay? They require energy, okay? So endothermic for both. That's a huge big idea in this in these first 2 units, really. Anytime you break a force of attraction, some energy is required to do that. It's an endothermic process, okay? So here's our starting point right here. You break your intermolecular forces or interparticulate forces in the solvent. It requires some energy. You break them in the solute, requires some energy. Then when the solute and solvent come together and dissolve, you make your solution. So you have a picture of it right here, okay? That's an exothermic process, okay? So you're forming exothermic, sorry. Okay, exothermic. Same up here, sorry. All right. So we want to, when we're forming attractions, right? When attractions are forming, that's going to release energy. Just like when you create, like when you make bonds, back in Unit 1, we talked about enthalpy of like covalent compounds, right? Enthalpy of formation of covalent compounds. When the covalent bonds were formed, that was a release of energy. Remember we did the bonds broken minus bonds formed problems? This is a similar situation here. We're breaking attractions, endothermic. We're creating new ones, okay, between solute and solvent, exothermic. What determines the enthalpy of solution is, does it take more energy to break all of your solute-solvent bonds than is released when you form your solute-solvent intermolecular forces, or is it the opposite? So you have your image here on the left. This is an exothermic enthalpy of solution. It took some energy to break your solvent attractions, some to break your solute attractions. But look, when you created your solution, there's a huge drop in energy, right? So it took X and Y, to break all those attractions, and then Z was humongous. So you had an overall, right here, you have an overall net release of energy, Okay? The opposite is true if it's an endothermic solution formation. So if you dissolve something and it gets cold, this is what's happening on the right. So you break your solvent interactions, put energy in. You break your solute interactions, put energy in. Look how much energy that took. Huge amount for that substance. And then look, when you created your solution, you still released energy. It's still exothermic. Right here, when you formed the bonds between solute and solvent, it just wasn't very exothermic. So you have an overall net input of energy. And a net release of energy is favorable. A net input of energy is not very favorable, but there's something else going on here that we'll talk about in our thermodynamics unit that allows this to happen, even though it's not favorable in terms of enthalpy. Okay, so that's you need to understand the difference between solute, solvent, and does it take energy to break or form? You know what I mean? Your interactions there. So it's always endothermic to break, exothermic to form. How much is required to do each? That determines enthalpy of solution. All right. Quick example here. I've dissolved 3 things. Okay. Sometimes in class I'll do this as a little mini demo or simulation. If I dissolve calcium chloride in water, temperature is going to go up. So I'm starting at, looks like 22 degrees Celsius for all of these, and calcium chloride ends up going up to around almost 25. Table salt, you have a small drop, and ammonium nitrate, you have a small drop as well. Okay, so calcium chloride would be an exothermic enthalpy of solution. Energy was released to cause the temperature of the water to go up. And then NaCl and ammonium nitrate, both of those enthalpy of solutions would be endothermic because it took energy in from the water to make those solutions. Okay, we'll talk more about that in thermodynamics, but this is a good little intro to it. And it's relevant because we're talking about solutions. All right, this is the really one of the last, this really is the last topic in the unit, I guess. How does solubility affect these different properties? Okay, so you have your conductivity, boiling point, freezing point, and rate of evaporation and vapor pressure. All of these properties are affected by the solubility of really anything. And we're going to do a little lab simulation on some of this to help us understand it. But these are really affected by either the total number of ions dissolved or total number of particles. Now, conductivity is a little different. Okay, if you dissolve something that is not ionic, like some covalent structure, if you dissolve something that's covalent in water, you're not going to increase your conductivity, right? But if you dissolve something that's ionic, and we talked about this before, if you dissolve an ionic compound in water, like table salt, you're going to increase the solubility, or you're going to increase the conductivity of that solution. I showed you in Chem 1 a little demo with that. Maybe you remember, with a little light bulb on the stand that I put the electrodes in, salt water, and it lit up very brightly. For everything else, boiling point, freezing point, rate of evaporation, vapor pressure, it depends on the total number of particles dissolved. So it could be something ionic, it could be something covalent, it could be something just that's polar. It's just particles in general. The only one that has to specifically be ions is conductivity. Okay? We'll talk about this in a minute here. 1 mole of sugar is 1 mole of particles. 1 mole of table salt is 2 moles of particles because you have 2 ions here, Na and Cl. And 1 mole of K2S is actually 3 moles of particles. You have 2 potassiums and 1 sulfide. Okay, so you have 3 moles of particles combining to make 1 mole of K2S. Okay, so within that 1 mole of K2S, you have 2 moles of K, 1 mole of S, 3 moles total. This is going to be important in a couple minutes. Okay, these are called colligative properties. Colligative properties are properties of a solution that depend on the concentration of dissolved particles right there. Okay, other than conductivity. Not the actual chemical itself. Again, other than conductivity. So a 1 molar solution of table salt, 1 molar solution of KBr, or a 0.5 molar solution of K3PO4 will have the same effect. So let's look at that. 1 mole of NaCl means you have 1 molar sodium and 1 molar, like 1 mole of chlorine, okay? So 1 molar is 1 mole per liter. So 1 mole of Na plus 1 per liter, 1 mole of Cl minus 1 per liter gives you a total of 2, right? Basically 2 dissolved particles there, like 2 moles of dissolved particles. KBr is the same way. In 1 molar KBr, you have 1 mole of potassium, 1 mole of bromide. So you get 2 particles again. All right. Now for K3PO4, the ions that make that up, I'll do it up here. You have K3PO4. You have 2 ions that make that up. Okay. You have potassium, K plus 1, and PO4, which is PO4 negative 3. Right. We have 3 potassiums and 1 phosphate. Notice how phosphate, it's not like you have 5 things in phosphate. Phosphate is the ion. So recognizing those in that nomenclature is really important here. So you have your phosphate ion, that's 1 chunk of, 1 molecule with the charge, of course, of P and 4 O's, right? That has the negative 3 charge on it. It's 0.5 molar. Okay, so you have 3 potassiums. That's a 3. Okay, 3 times 0.5 molar, okay, gives you 1.5, right? 1.5 for your molarity there, basically, because you have a half a molar solution. So you do a half a molar times 3. Phosphate, there's only 1 of them, so it's another half a molar, right? 1.5 plus 5 gives you 2, right? So 2 moles of dissolved particles, basically. 2 moles of dissolved particles for NaCl. 2 moles of dissolved particles for KBr. Okay? All of those will have the same exact effect on all of these colligative properties. Okay? Because you end up with 2 moles for all of them. Okay? So this is pretty easy, actually, once you get the hang of it. We'll do an example in a minute. Our lab is going to really, solidify this for us. The lab involves boiling point elevation and freezing point depression. You really want to focus on moles of particles, right? That's what I just did, not mass. If you're given the mass of something, you want to convert it into moles and then convert it into moles of dissolved particles. And we're going to do, like, this is a screenshot right from the lab. You guys will be doing that in class, either already or at some point in time. So how does boiling point elevation work? Here's your regular water that's boiling. Okay, so there's normal vapor pressure of water. Okay, you have your your water molecules moving relatively fast, and they escape, right? Well, notice on this one here, we dissolved something in it, maybe table salt. So you have your ions floating around in there. When your ions are floating around in here, what do we also have? We only over here do we have hydrogen bonding. That's all we have. Here we have the hydrogen bonding in the water. That's the normal intermolecular force. You also have an ion, like dipole force here, right? The ion from the NaCl, like the ion from those ions, making an attractive connection there with the dipole moment that water has. So that's your ion dipole force. That's a pretty strong force of attraction here. So you're going to have a lower vapor pressure above the solution here, okay? So, some people think you put salt in water before, like when you're making your pasta. You're trying to boil your pasta to make it taste better, which it might have some, improvement of flavor, right? Because you're putting salt in the water. But it really causes it to cook faster, because when you add salt to water, it doesn't boil as easily. So what has to happen? You have to make that water hotter, okay? In order for the water to boil, it needs to be at a higher temperature when you dissolve the salt in it. Okay, so it's not really for the flavoring effect, it's to cook it at a faster rate, okay? So you're going to be cooking it at a higher temperature. Here, with no salt, water boils at 100 Celsius. Your pasta cooks at 100. Here, depending on how much salt you add, your pasta might be cooking at 103 degrees Celsius, right? So it'll cook faster. Because of those ion dipole forces of attraction, keeping the water molecules in the solution and not having them leave as easily, because they have to break that extra attractive force now that they didn't have to over here. All right, so to wrap it all up here, your colligative property is boiling point. The effect of adding dissolved particles increases your boiling point. So I already talked about that in the previous slide. This is called boiling point elevation. Salt water boils at a higher temperature, cooks food faster. So just talked about that. The reason being is you're creating ion dipole attractive forces now in your solution, and the water has to move faster to break those and escape to evaporate, right, and to boil. Freezing point is actually going to decrease if you add dissolved particles, called freezing point depression. So this is why you add salt to roads in the winter. I should say in winter. Okay. In the wintertime, you add salt to roads, and they don't freeze up as fast, right? Or they don't freeze up, or just really in general, unless it's really, really, really cold. How does that work? You add, let's say salt, right? You're adding salt. You're adding these ions to the snow, which is water, right? So again, you're creating, just like in the boiling point elevation, you're creating ion dipole attractive forces, right? So you have these ions in there now, and it's harder for the water molecules to be attracted to other water molecules and freeze, okay? It's harder for the water molecules to be attracted to other water molecules because there's other stuff in the way, right? You have your ions from the salt in the way. So you don't get those connections made as well, so you don't have freezing, okay? So you have this basically salt water solution on the roads that prevents the freezing from occurring, which is good because that makes the roads obviously safer to travel on in the winter. And sometimes you'll even see the PennDOT salt trucks, like they put down a spray first, right? And then later on they'll put down some of the solid salt as well, once you have that wetness on the road already. Okay, vapor pressure is going to decrease. Here's why. It all goes to, like these other two, all goes to the point of you adding an impurity to your solution, right? So the impurity, which is, let's just say salt, means there's less solvent particles at the top layer to evaporate. It also keeps the stronger solvent-solute interaction. If it's an ionic compound you're dissolving, that's your ion dipole force. Keeps more molecules in solution. So vapor pressure, you need to have a higher vapor pressure. You need more particles in the vapor phase, in that gas phase. If there are less solvent particles at the surface to evaporate, less will be in the gas state. Also, if you have these ion dipole or just solute-solvent interactions, it's harder for them to break and for you to create gas particles, right? So your vapor pressure is going to decrease. And then conductivity, we talked about that a couple times already. It's only affected if the solute is ionic. That is going to increase. So the more salt or the more ionic compound you add to a solution, the greater the conductivity is going to be. So you have more charged particles and ability for electrons to flow. So to wrap it up, this is the last slide. An aqueous solution of 1.5 molar NaCl has a boiling point of 101.4 degrees. What aqueous solutions of the following will have the same boiling point? Okay, so we have calcium chloride, copper 1 nitrate, iron 3 chloride, and nickel 2 sulfate. What molarity of these, each one, would you need to have the same effect on the boiling point as 1.5 molar NaCl? This goes all the way back here to this slide. So remember, the 1 molar NaCl, the 1 molar KBr, and the 0.5 molar K3PO4 will all have the same effect because we want to find the same number of dissolved particles. Okay? Let's do that for this example. Sorry. How many dissolved particles does 1.5 molar NaCl have? And then what would the molarity of these things need to be to have the same number of dissolved particles? Okay? Pause the video, give it a try, and we'll go over it to wrap up the lesson. Okay, so you have 1.5 molar NaCl. That means you have 1.5 molar sodium ion, and you have 1.5 molar Na, and you have 1.5 molar Cl. So your total dissolved particles here is 3. Okay? So that's our goal here. We get 3 dissolved particles, right? Because the NaCl would dissociate into Na+1 and Cl-1 in solution, right? So you get 1.5 molar Na and 1.5 molar Cl to give you 3 particles total. So let's look at calcium chloride. It's, let's do the formula over here. Calcium chloride is CaCl2, right? So let's look at how many dissolved particles we would have here. So we have 1 calcium and 2 chlorides. Okay, so 3 dissolved particles here. 3 times what would give you 3, right? So we want to know what's our molarity going to be. Well, if we have a 1 molar solution, I'm going to have 1 molar calcium, 2 molar of chloride, right, to give me 3, right? So that's what I need for the calcium chloride. 1 molar calcium chloride would dissociate into 1 mole of calcium, 2 moles of chloride, give me 3 moles of dissolved particles. Next one, copper 1 nitrate. So copper 1 nitrate is going to be CuNO3. Now be careful here, because nitrate is an ion. This stays together, right? So the nitrate, NO3-1, is, a charged molecule floating around in solution, and the Cu+1 is also just 1 dissolved particle, okay? So how many dissolved particles do we have here? We have 1 dissolved particle with copper, 1 dissolved particle with nitrate. So 2 dissolved particles. What do I need to multiply 2 by to get 3 total dissolved particles? Well, I need a 1.5 molar solution. Notice this is the same exact scenario. You had 1 dissolved particle with Na, 1 dissolved particle with Cl, 1 dissolved particle with copper, 1 dissolved particle with nitrate. So you need a 1.5 molar solution to get 3 moles of dissolved particles. So this is the same as the NaCl. Your positive and negative ion is just 1 dissolved particle each. Okay. Iron 3 chloride is FeCl3. So hopefully you're getting the hang of this by now. How many dissolved particles do you have here? You have 1 from iron and 3 from chloride. Gives you 4 dissolved particles total, right? So 4 times what is going to give you 3 dissolved particles? Well, if we do 0.75 molar iron 3 chloride, 4 times 0.75, 4 times 3/4 gives you 3 dissolved particles, right? So we want a 0.75 molar iron 3 chloride solution. 0.75 from the iron, and then 0.75, 0.75, 0.75. That gives you 2.25 from the Cl. Okay, 0.75 times 3. Finally, nickel 2 sulfate. Nickel 2 is a +2, sulfate's a -2, so you have NiSO4. If you notice, the nickel is 1 dissolved particle, the sulfate is another one, so you have 2 dissolved particles. It's the same as copper nitrate, it's the same as NaCl. You need a 1.5 molar solution. 1.5 times 2 dissolved particles gives you 3. Okay? Alright guys, that was a pretty long lesson, but it was 3 really short lessons back to back to back. So there's 3 10-minute lessons plus this little practice problem here. That takes care of the unit. So if you need any help, let me know, and hope this made sense to you guys. Alright, thanks.